Alright, so here are the test solutions. Hopefully these are all right. Check these out, you'll do well on the final. Alright, is the above chart endo or exothermic? The products are below the reactants. That means it loses energy, which means it is exothermic. The products have less energy than the reactants, right? We see that. This is a negative delta H. This triangle right here just stands for delta. A catalyst would require this less activation energy. That's just the that is simply the definition of a catalyst. It would make it look sort of like this, right? It wouldn't have to go all the way up to this peak at 103. You could stay right around 60 or 50 or something like that, just like that. Oh, I just did that. So here's the dotted line to show the catalyzed reaction. Number 5, how much energy do reactants begin with? We can just look right here, 45 kilojoules. 45 kilojoules. How much total energy is lost in the reaction? It goes from 45 to 10, so that is a 35 kilojoule loss. How much activation energy is needed? It goes from 45, and the activation energy is all the way up here at 103. So 45 to 103. I can't do that in my head. I guess I can. It's like 58. Let me see. That's right. It requires 58 kilojoules. 12 grams of NaCl dissolved in 370 milliliters of water would be a blank molar solution. 12 divided by 58, so we can find our moles. Equals 0.21, and then we're going to do our moles divided by liters. So that's 0.37 liters. 0.37. I'll write it like this so you guys can understand it. Equals x over 1,000. That's just what I did right there. Right? I just simplified it a lot. And we end up with 0.56 molar. 5 grams of Cl2 dissolved in 101.2 liters of water would be a 5 divided by 70. This is equal to 0.071 moles divided by 101.2 liters. It's equal to 0.00071 molar. Right there. Moving on. For the honors kids, 300 milliliter of 3 molar CAS solution is diluted with 25 milliliters of water. What is the new molarity? Well, this is really easy. We're going to do 3 times 0.3 equals M times 0.325. This is just this equation right here. And you can see that right there. M1 V1 equals M2 V2. And I'll write that. Well, this is our new volume right there. Just that equation right there. So our new M is equal to 3 times 0.3 equals divided by 0.325. So our new M is equal to 2.77 molar. According to Henry's law, the amount of gas dissolved in solution would increase or decrease as the pressure increases. It would increase. Remember, because that's S over P equals S over P. So as the pressure increases, the solubility would increase. That's just this relationship right here. If 0.005 grams of a gas are dissolved in a liter of water at 800 millimeters of mercury of pressure, how many grams would be dissolved at 900 millimeters of mercury pressure if the temperature didn't change? I just wrote that equation out here above, but let's write it down here. 0.005 over 800 equals x over 900. So we're just going to do this times 900 divided by 800. It would equal 0.0056 grams per liter. Right, so that's a little bit more. All right, 7 atmospheres of pressure and negative 75 degrees Celsius would be what phase of matter? All right, so right away we need to label this. This is labeled in Greek, so let's go solid, liquid, gas. This is the triple point. This is the critical point. Critical zone, really. I don't think I need to label that though. 7 atmospheres of pressure. Let's see, the 7 is right about here, and negative 75. Label that, that's 0.14. That would be solid. 12 atmospheres of pressure, and negative 50 degrees. That'd be like right there. That's number 15, liquid. Going from 0.14 to 15, solid to liquid, melting. What is sublimation? Solid to gas. All right, a hot piece of metal is dropped into cool water. What happens according to the laws of thermodynamics? Write 3 or 4 sentences. I'm going to pause this real quick and then show you my sentences after. Okay, so there's a couple of different ways to word this, but essentially here's what my answer is. The hot piece of metal does not stay hot, neither does the cool water stay cool. The metal transfers its heat to the water. This is happening according to entropy. Remember, when we talked about entropy, we used a different example where I put a ice cube in a warm water, right? It's going to transfer the heat. The warm water is going to transfer the heat into the ice cube. So this entropy just is the state of chaos, right? And this transfer of heat is according to entropy. And then the heat is then stored into the water. It is not destroyed. This is according to the first law. All right, here we go. Exothermic reactions have a negative delta H. We can see this in front of the page, right? This right here was an exothermic reaction. It lost energy, so it has a negative delta H. Endothermic reactions feel cool to the touch because it's drawing in the heat. It's drawing in the heat from your hand. If something feels cold, is it taking in or giving off heat? It is taking in heat. Right? Moving on. If a reaction occurs and the product contains more energy than the reactants, the reaction was endothermic. It is the opposite of what happens right here. If the graph would look like this. It'd start here, activation energy, and end somewhere like that. That's endothermic. Specific heat. How much energy is required to heat 45 grams of water from 140 degrees Celsius to 143? All right, so if this water is already at 140 degrees Celsius, we know it is steam. So let's look at our specific heat for steam, 2.02. Let's write our equation. Q equals 45 times 2.02 times, and our delta T is 3 times 3. 45 times 2.02 times 3. It takes 272.7 joules per gram degree Celsius. Remember, that's our units. Or no, that's just joules. Excuse me. I was wrong, but this is right. 2,951 joules of energy are used to heat up 212 grams of a metal from 30 degrees Celsius to 20 or 61. What is the name of the metal? Okay. So now we're looking for the specific heat. So let's do 2,951 is equal to 212 times, we're looking for the C, times, and that is a change of 31. All right, so let's do 2,951 divided by, in parentheses, 212 times 31, in parentheses, equals, our C is equal to 0.449, and let's look on our table for 0.449. It's right here. That's iron. That is iron. You lay a chunk of aluminum out in the sun beside a chunk of copper. Which will heat up fastest? Well, let's look at our specific heat. Our aluminum specific heat is 0.897, and our copper specific heat is 0.385. So, knowing what we know about specific heat, that means that it takes less energy to heat up copper per gram per degree Celsius, right? Because that's the unit of specific heat, but also it's less than the aluminum. It is less, so the copper would heat up much faster. So the copper is fastest. All right. Solubility. 20 grams of aluminum chloride is dissolved in 100 grams of water at 20 degrees Celsius. Let's find aluminum chloride. I cannot. Ammonium chloride. Oh my gosh. Okay. Ammonium chloride. There it is. Ammonium chloride. So 20 grams of ammonium chloride, 100 grams of water at 20 degrees Celsius. So 20 degrees Celsius, ammonium chloride is right there at 20. So of 20 grams, that's right there. That looks like that is an unsaturated solution. 70 grams of NH3 is dissolved in 100 grams of water at 10 degrees Celsius. Let's look at NH3, 70 is right there. There's 10, that is a saturated solution. 70 grams of ammonium chloride is dissolved in 100 grams of water at 80 degrees Celsius. So back to the ammonium chloride, 70 grams at 80. That looks to be super saturated. On to the back. All right, we got just how do you make a super saturated solution? So this is not an honors question. This is a regular question. I'm going to go ahead and answer it down here. Heat up the solution so it accepts all, oops, I spelled all wrong, all of the solutes. Then cool down the solution. The solutes will remain, and the solution will be super saturated. This is number 30. Okay, so heat up the solution so it accepts all the solutes, then cool down the solution. The solutes will remain and the solution will be super saturated. I know my handwriting is terrible. Hopefully you can read that. I'm going to answer these honors essay questions real quick, or short answer, not really essay. And I'm going to pause it, and then I will show you guys the answer. Okay, so I have my answers written out for this. Number 31, explain what a catalyst is. Give an example of a catalyst in real life. So a catalyst lowers the activation energy in a reaction. You could have gotten that from the first question, or number 4. The catalyst would make less activation energy. I mean, the answer is already on the test. And the catalyst was the salt in the copper and aluminum lab. That was a catalyst. Remember that when we put the temperature probe in the salt, we put the temperature probe in the solution with the copper sulfate and the aluminum, and then we put salt in it, and we could see the copper sort of plating the aluminum in the temperature probe. The salt was the catalyst. Number 32, explain entropy in 3 or more sentences. Well, I got a little wordy, but hopefully this makes sense. Entropy is the measure of disorder. It means all things in the universe tend to move towards chaos. They don't stay isolated within their own system. For example, a hot cup of coffee doesn't stay hot forever. The heat will dissipate into the environment. Hopefully that makes sense, but it's kind of difficult to think about. But I really want you guys to understand that, like, a hot cup of coffee, and think about it this way, it's what helped me out, but a hot cup of coffee, it's not just its own thing, right? The hot cup of coffee is always interacting with its environment around it, okay? So the hot cup of coffee, the heat is going to leave it, and by the heat leaving the cup of coffee, by the energy leaving the coffee and dissipating out to the universe, that is called disorder, that's called chaos. So an example of not disorder would be like if you poured yourself a cup of coffee, put it on the table, and it stayed hot forever. That is order. That is not chaos. But chaos is the opposite of that, and chaos is what we see in real life. Hopefully that makes sense. Cold does not exist. It is just a word. Explain. Well, Mr. Perkins went very theological with this one, but let's see if this makes sense. All things have heat because all molecules are moving constantly. Think of the kinetic molecular theory. The only thing that could be cold is absolute zero, which would be no movement. But since that is impossible, cold does not exist. Remember, heat is the measure of the movement of the molecules inside of an object. If all things have movement, then all things are hot. Some are just not as hot as the other. So if you were to anything like that, and if you mentioned the kinetic molecular theory and absolute zero, you're on the right track. So that is the test. Go back and rewatch anything you might have questions on, and call me out if I'm wrong. Thank you for watching.